Welcome students, and this is Ravi Shankar. See, in our last video regarding the fourth lesson, we have studied about the laws of electromagnetic induction. Regarding the laws of electromagnetic induction, I have stated some 4 laws. Out of that 4 laws, the 2 laws are considered to be Faraday's laws of electromagnetic induction, from which we can able to say when you can able to get an EMF and how much amount of EMF can be got. Then the third law is considered to be the Lenz law, which gives you the direction of the EMF that was being induced. And the fourth one also gives you the direction where the EMF is induced, but that law is given by another scientist called it to be Fleming, and we named that law as Fleming's right hand rule. Already we have proved the Faraday's first law as well as the second law. Faraday's first law states that whenever there is a change in the magnetic flux linked with a coil or a conductor, an EMF is induced. Faraday's second law states that the rate at which the magnetic flux is changing gives you the magnitude of the EMF induced, or we can say the magnitude of the EMF induced is proportional to or equal to the rate at which the magnetic flux is changing. And we might have derived a relation E proportional to d phi divided by dt with a negative sign. The negative sign gives you the direction. That direction was stated by or given by Lenz. See, in your book it was being given as a German scientist, but actually he is a Russian scientist. So what about this Lenz law, or what that Lenz law states? In our last class, last video itself, I have given the Lenz law. Again, in order to get the Lenz law and what is the purpose of the Lenz law and how we can able to prove it out, all that can be done with the help of 2 illustrations. So first of all, let us state the law. What is the Lenz law? Lenz law states that the EMF induced or the current induced is in the conductor or in the coil is in such a way that, or in such a direction that it always the opposing the EMF, it always opposes the change in magnetic flux, or always opposite to that of the cause. That is considered to be the law. So the law states that the direction of EMF or current, the direction of EMF or current induced is always in a direction, opposite to that of the cause, opposite to that of what? Opposite to that of the cause. What is the cause for producing the induced EMF or current? The cause is change in magnetic flux. The direction in which the flux changes, opposite to that direction, the EMF or that current will be induced. That is, the induced current or EMF flows in a direction opposite to that of the direction in which the flux changes. So that we are considering it as the law. If you want, you can write an explanation. That is, I can say the induced current or EMF, induced current or EMF always flows in a direction, opposite to, opposite to the direction in which the flux changes, direction of change in flux. Direction of change in flux. This is considered to be the explanation, just a small explanation. How you can prove or how you can illustrate with the help of an experiment or with the help of an activity that the EMF induced is always in a direction opposite to that of the direction in which the flux changes or direction to the cause. So there are two illustrations given in your book, and let us consider the first illustration. So the illustration 1. So in order to consider an illustration 1, I am taking an uniform magnetic field. So I am representing the uniform magnetic field by crosses. See, if you are representing a uniform magnetic field, along the plane of the paper, parallel lines will be drawn. If you are drawing the uniform magnetic field or representing the uniform magnetic field B with the help of crosses, then it indicates that the magnetic field B is acting, perpendicular to paper. It is acting perpendicular to paper and inwards. It is acting perpendicular to the paper or perpendicular to the board and acting in the inwards. That was being represented by drawing what? Represented by drawing crosses. Now, inside this uniform magnetic field, I have placed a rectangular frame. Okay, I have used another color. So there is a rectangular frame placed inside. In this rectangular frame, I am having the closing end represented as AB. This closing end AB can able to slide over this rectangular frame either inwards or outwards. See, this closing end AB can move inwards or can move outwards. Let us consider this rectangular frame as A, B, C, and let us take this as or let us take this is A, this is B, this let us take C, and let us take this as D. Okay, so already we have used B, so let us take this as D. So ABCD is a rectangular frame which is placed inside that magnetic field, and the end AB is free to move. Either it can able to move inside or outside. By moving this frame AB inside, the area can be decreased. When the area is decreased, the flux can be decreased. So I can produce a change in flux. Similarly, when I am taking B to the outside, then I can say the area increases. If area increases, flux increases. So there is a change in flux. Then also I can able to get an EMF. Let us demonstrate how we can able to get this. See, first one, the first point, let us take like this. Initially, okay, initially the end AB is at rest. If the end AB is at rest, let us take this diagram as number 1. When this end AB is at rest, then we can say there is no change in flux. There is no change in what? There is no change in flux. If there is no change in flux, then no current or no EMF is induced. No current or no EMF is induced. Let us consider this as the first point. What is the second one? What I am going to do? The second one, I am going to move this conductor AB to the right of it so that the area enclosed by this rectangular frame can get increased. So I am taking it as the next point. So I am writing it here. See, when I am taking the second point, What is the second point? See, the point number 2 is, again, I am considering that uniform magnetic field which is acting perpendicular to the paper and inwards, which is represented by drawing what? Which is represented by drawing crosses. Inside this uniform magnetic field B, which is acting perpendicular to the paper and inwards. Already we have stated there is an rectangular frame placed, and that rectangular frame placed is taken to be this end. We are having that conductor A, moving conductor AB, and the other end is CD. Now what I am taking this conductor from this original position to a new position. I am moving this conductor to the right of what? To the right of the original position. So the second concept, what is the second concept? By moving the movable end AB to the right of the original position, to the right of original position. What I can do by moving that conductor AB to the right of the original position, the area enclosed increases. See, if the area enclosed increases, what will happen? Then the number of lines passing through that area increases. If number of lines passing through that area increases means, then we can say the flux increases. So due to this, what happens? Due to this action, or due to this cause, this is the cause. Due to this cause, the flux increases. Due to this cause, the flux increases. So due to INCREASES, okay, the flux increases. When you are considering the flux increases, what happens? Due to this cause, what happens? EMF or current is induced. What will happen? The EMF or the current induced will try to decrease that change, because this EMF induced or current induced, according to Lenz law, acting in what direction? Acting in the opposite side direction to that of the cause. So I can say this EMF or the current induced produces another magnetic field, which will produces another magnetic field, which will try to decrease that flux, which will try to oppose or oppose the existing magnetic field, which will try to decrease the oppose the existing magnetic field. So a magnetic field is developed due to what? Due to this EMF or the current induced. That EMF or the current induced, according to Lenz law, acting in the opposite side direction to that of the direction in which a flux changes. So the flux is increasing, but the current induced or the EMF induced will try to produce another magnetic field or flux, which will be trying to decrease the change. So that is what I have written. The EMF or the current induced produces another magnetic field, which will try to what? Which will try to oppose the existing magnetic field. The existing magnetic field is acting perpendicular to the paper and acting in inward direction. This induced EMF or the induced current will be now developing another magnetic field, which will be in the direction opposite to that of the existing magnetic field. Means then the new magnetic field produced will be perpendicular to the plane of the paper, but in the outward direction, because the existing magnetic field is in the inward direction. So the new magnetic field produced is represented by the red dots. If I am marking the new magnetic field with the red dots, means the red dots are indicating the magnetic field is acting perpendicular to that of the paper and outwards. Are you able to understand? See, now the red dots, I can write the red dots marked. Red dots marked will try to, or we can say the red marks mark represent, not will try to, let us write represent, okay, represent the magnetic field B acting perpendicular to paper and outwards. So outwards. Now by knowing what? By knowing the direction of the magnetic field, I can say the direction of the induced EMF or the current by the right hand thumb rule. So with the help of the right hand thumb rule, I can say that the direction of the induced EMF or the current is in anti-clockwise direction. What is the right hand thumb rule? See, when you are considering the right hand thumb rule, we can say like this. When you are considering this thumb rule, the thumb will be giving you the direction in which the magnetic field is acting. The magnetic field is acting outwards. So the folded fingers will be giving you, or the folded fingers will be giving you the direction of the current. The folded fingers is in anti-clockwise direction. So I can write by knowing. So here I can write by knowing the direction of the magnetic field. By knowing the direction of magnetic field using right hand thumb rule. Using right hand thumb rule, we can say the direction of induced current. So by knowing the direction of the magnetic field using right hand thumb rule, it was found that the induced current or the EMF, the induced current or EMF is in the anti-clockwise direction. EMF or current or EMF is in the anti-clockwise direction. Anti-clockwise direction. Hope you should have understood. See, I will be recalling. What is this illustration? When that sliding conductor AB is moved to the right, then the area enclosed by that rectangular frame increases. When area increases, then magnetic flux increases. When magnetic flux increases, due to the change in magnetic flux, an EMF is induced. The EMF induces always in a direction opposite to that of the cause. So the magnetic flux increases means towards right means then the EMF induces towards left. That EMF induced or the current induced will try to develop another magnetic field which will be opposite to that of the existing magnetic field. Because the EMF induced or the current induced in the opposite side direction to the cause. The existing magnetic field is acting perpendicular to the board or perpendicular to the paper and inwards. So the new magnetic field produced by the induced EMF or the current is perpendicular to the paper and outwards, which I have marked it with dots and red color. Now, by knowing the direction of the newly developed magnetic field, I can able to calculate or I can say the direction of the induced EMF or the current with the right hand thumb rule. See, the thumb gives you the direction of the magnetic field which is acting perpendicular to that of the plane. Then what happens? And outwards. If it is like this, it is acting in the inward direction. So it is acting in the outward direction. If it is acting in the outward direction, then the folded fingers will be giving you the direction of what? The folded fingers will be giving you the direction of the induced current or EMF. The folded fingers are considered to be in anti-clockwise direction. So we can say the induced current or the EMF is in anti-clockwise direction. Hope you should have understood. This is the second point of first illustration. Now, let us move on to the third point of this illustration. what I am going to illustrate now. Again, you consider the same concept, that is a uniform magnetic field is represented by drawing crosses, which indicates that that uniform magnetic field is acting perpendicular to the paper and inwards. Let us consider that uniform magnetic field as B. Now inside this we are having what? We are having an rectangular frame, and in this rectangular frame the end A, this end B, which contains the movable conductor. Let this be the original position, and let us, these ends are considered to be CD. Now what I am going to do? What I am going to do in the third point means I am moving this sliding conductor AB to a new position towards the frame or inwards in the frame, so that the area enclosed by the frame is decreased. So here in the third point I am saying AB is moved towards left, so that what happens, the area enclosed by the frame, or enclosed in the frame decreases. So what happens if the area decreases by moving it towards the right? Then we can say the magnetic flux also decreases. So if you are considering magnetic flux also decreases, then there is magnetic flux decreases means there is a change in flux. Due to the change in flux, what will happen? An EMF or current, is induced. Because of what? Because of this change in magnetic flux. In what direction this EMF or current is induced? Let us see later. How? Because this EMF or the current induced now develops a new magnetic field. In what direction this magnetic field will act? This magnetic field will now try to increase the original magnetic field because the flux is decreasing. According to Lenz law, if flux decreases, then it should opposes the cause. So because of that, we are getting EMF. That EMF should develop a magnetic field which opposing the decrease. Which opposing the decrease means the new magnetic field develops should get what? It should get increased, which is in the same direction as that of the existing magnetic field. See, existing magnetic field is perpendicular to the paper and inward. Now the new magnetic field, again I am representing with the red color, but here it is again acting in the same direction of the original magnetic field. So I am representing it as crosses perpendicular to the paper and inwards, so that what happens? So that we can say that this magnetic field newly developed can able to oppose the decrease in magnetic field. So in what direction the EMF or the current is induced? By knowing the new magnetic field, I can say the direction of the EMF induced. What is the direction of the newly developed magnetic field? It is perpendicular to the paper and acting inwards. Use the right hand rule. When you are using the right hand rule, the thumb gives you the direction. There you can able to get the direction of the newly developed magnetic field. Then the folded fingers are giving you the direction of what? The folded fingers are giving you the direction of the induced EMF or the current. The folded fingers are in the right hand direction, so in the clockwise direction. So the direction of the induced EMF is in the clockwise direction. Now I can say that now it develops a new magnetic field which is perpendicular to paper and inwards, which will try to increase the flux. Okay, which will try to increase the flux. So if you are decreasing the flux, then according to Lenz law, the opposing is increasing. So the EMF induced, or we can say the induced current, will develop a new magnetic field which will try to increase the existing magnetic field by acting perpendicular to the paper and inwards again, represented by crosses in red color. So using what I can do now? Now using right hand thumb rule, using right hand thumb rule, we can say that the direction of EMF or current induced is the direction of EMF or current induced is in clockwise direction. In clockwise direction. So this we are considering it as the first demonstration which illustrates that the EMF induced is always in a direction opposite to that of what? Opposite to that of the cause. Any difficulty? So this is considered to be the first illustration which proves or which illustrates Lenz law, which is stating that the direction of the EMF induced or current induced is always in a direction opposite to that of the cause or opposite to that of the direction in which the flux changes. Let us move on with the illustration 2. Now, let us prove or let us illustrate the Lenz law with our second illustration. So, in order to get that second illustration, you consider a coil of wire as we have considered in Faraday's experiment, and the ends of the coil are connected to a galvanometer which can indicate whether there is a flow of electrical current or not. Nearer to that of the coil, you keep a magnet. As long as this magnet is kept stationary, there is no deflection in the galvanometer, indicating that there is no flow of electrical current in it. What I am going to illustrate here. You see, again, I am considering this coil of wire alone. The ends of the coil are connected to the galvanometer. I am placing the magnet here. One end of the magnet, I am taking it as the north pole, and another end, I am considering it as the south pole. As I have already told you, as long as the south pole as well as the north pole of the Bohr magnet is kept stationary, the magnetic flux linked with this coil, let us consider this coil as C, never changes. But if this magnet is moved towards or if it is taken away, then we can say that there is a change in flux. If there is a change in flux, then this galvanometer will be producing what? This galvanometer will be producing an momentary deflection. When you are moving towards, it will deflect towards one side. Then again it will come to zero. When you are taking it away, the deflection will be on the other side, and then again it is coming to this zero. So now, how I can able to illustrate this Lenz law using this? See, the first concept, I am taking this north pole towards that of this coil. When I am taking this north pole towards that of the coil, there is a change in flux. Due to the change in flux, there will be what? Due to the change in flux, there will be an induced EMF or there will be an induced current. This induced EMF or the induced current will oppose what? Will be opposing the change in the flux. Due to this induced EMF or the current, you will be able to get the coil to be acting as an magnetic dipole. See, because of this induced current or EMF, this coil will develop a magnetic field, so that the coil is acting like, so that it acts like an magnetic dipole, If it is acting like a magnetic dipole, means at one end you will be having the north pole and at the other end you should get the south pole. See, according to Lenz law, the EMF induced should oppose the magnetic change in magnetic flux. Then what should happen? then the nearer end of this north pole in this coil, the nearer end of the coil which is nearer to that of the north pole should get north pole again, and the other end should get south pole. So what will happen? This north pole, due to the induced EMF or the current, opposes this motion of the magnet. So if you want to move the magnet, we have to use an external force. Otherwise, or external work done. Otherwise, the magnet will get what? Due to this north pole and this north pole, this magnet will get repelled. Clear? But at the same time, if you are withdrawing this magnet away from what? Withdrawing this magnet away from this end, what will happen? You see, let us consider then another diagram. When you are considering a coil of wire, okay, I am having the coil of wire. The end of the coil is connected to the galvanometer. The coil is C. Here I am placing what? Here I am placing the magnet, and the magnet is having the north pole here and the south pole here. What I am going to do is, now I am taking the magnet away from this coil. When I am taking the magnet away from coil, that is, I am taking magnet away from coil. See, when the magnet is taken away from the coil, again what will happen? The flux changes, the flux gets decreased. So the magnetic field should get increased. If I am taking away, the magnetic field that is developing in the coil should pull this magnet towards in order to increase the magnetic flux. So if I am taking it away, the EMF or the current that is induced, EMF or the current induced, should act in a direction in such a way that it develops a magnetic dipole in the coil, having the south pole at this nearer end of the magnet and the north pole at the other end. Then only this south pole can pull this north pole, so that the flux, decrease in flux, opposite to decrease in flux is this coil should try to increase the magnetic flux. So by attracting, the flux can get increased. If you can able to know the direction in which the magnetic field is produced, then using the right and the thumb rule, we can always, or we can able to calculate the direction of the induced current or the induced EMF. See, in the first case, you see, when you are taking the magnet towards the coil, in the first case, you see the direction in which the magnetic field is towards, then flux is increasing. If flux is increasing, then there should be a repulsion. If there is a repulsion, the magnetic field is acting from what? The magnetic field is acting from north. That is, the induced EMF or the induced current in the coil produces a magnetic field which opposes the motion of the magnet. Which opposes the motion of the magnet means then the top end of the coil should have north pole. So the north pole developed in the coil will oppose the north pole of the magnet. So what will happen? Then what will happen? Automatically the flux will get decreased, because by moving the coil, the flux will try to increase. But according to Lenz law, it should get the induced magnetic field should oppose it, so that the flux will decrease. The similar explanation can be given for what? Similar explanation can be given for the other one, the third one also. What is the next one? That is, when you are moving the magnet towards, then flux increases because the magnet is moving towards the coil. But due to the change in flux, an EMF is induced. That EMF induced should develop a magnetic field in the coil which should oppose which would oppose means the decrease in magnetic flux should get increased. For that, the magnet should curve towards. So in that coil, the top end will have the south pole and the bottom end will have the north pole. By knowing the direction of the new magnetic field developed in the coil, using the right hand thumb rule, the direction of the EMF induced can be found in the coil. So we can write, what is the conclusion? So we can write using the right hand thumb rule, using the right hand thumb rule, we can determine the direction of we can determine the direction of induced current or EMF, or induced EMF or current by knowing the direction of new magnetic field developed. So with this, or from this illustration, again it is proved that the direction of the EMF or the direction of the current induced is always in a direction opposite to that of what? Opposite to that of the cause, or opposite to that of the direction in which the flux changes. Hope you should have understood, and let us meet in the next video. Until then, goodbye. Thank you.